नमस्ते बच्चों, हमेशा खुश रहो. Myself Dr. Monica Trivedi, and today's class topic is molecular orbital theory. So the molecular orbital theory results from the combination of atomic orbitals A.O.s and to form a M.O.s molecular orbital. Since these orbitals are a wave function, they can combine either constructively to form a bonding molecular orbitals or destructively, like the formation of the antibonding molecular orbitals. So as we consider the H2O molecule, for example, this is the molecule orbit. In this molecule, the constructed by the adding the mathematical function for a 2,1s atomic orbital that come together to form a molecule. The another orbital is formed by the subtracting one of these function from the other. So here you can see for the bonding is A plus B, and for antibonding is A minus B. The two s orbital, 1s and 1s, the two electron present in this orbital. So one is for bonding and one is for antibonding. So you can see here the 1s, one electron in both orbital, s orbital, and two electrons in a sigma 1 s orbital, and there is no electrons in a sigma 1 s star orbital. So the bonding molecule orbital theory, this kind of bonding orbital result in the increased electron density between the two nuclei, and this is the lower energy than the two separated atomic orbitals. There is the energy of the two orbitals, and by the overlapping of these orbitals, the density of electron presence is enhanced. Now, in a bonding molecular orbital theory, the antibonding orbital results in a node between the two nuclei and is of the greater energy than the two separated molecular orbital. So in this antibonding, the two molecular orbitals, the atomic orbitals cannot overlap with each other, and there is a less chances to present the electrons in there. So there is a presence of node in this kind of overlapping. Now you can see the overlap of the s and p orbital here. In first example, you can see the two s orbital for out of the phase or for in of the phase. You can see the plus sign for sigma 1 s for the bonding, and you can see the plus and minus sign for the sigma 1 s star. Okay. For the second kind of interaction, you can see here that the 2px and 2px of p orbitals, two of p orbital are combined with in phase, and out of the phase it will give sigma 2p for bonding and sigma 2p star to sigma star 2p for the antibonding. Okay, now for the 2py orbital, for 2py orbital, you can see here for the in phase and the out phase, the nuclei is for this kind of compound. You can see here the 2p bonding and pi star 2p for the antibondings. So the sigma bonding of the orbital, to form a sigma bond, there is an s orbital on the separate atom, the s orbital, two s orbital, and to form the sigma bond orbital, the molecules are obtained like this, plus and plus, and it will get the sigma bond. Okay, now for the molecular orbital theory of the second energy level, if we attribute that behind the z-axis is the coordinated system for the O2 molecule, as the axis along with the bond form. The 2p-z orbital on the adjacent atom will meet hand on to the form and form the 2p bonding and a 2p star antibonding molecular orbital. So you can see here the 2p Z orbital, 2p Z orbital for A and B. Here we will find the two M.O.s for bonding and antibonding with sigma 2p bonding and sigma star 2p for antibonding. So the sigma bonding or orbital of p bonding, like the 2p orbitals, they will combine and form the sigma bonding molecular orbitals. Now for the 2px orbital, the one of the interaction is the 2px orbital of the form is another form is to be the different shape. So this kind of interaction called as a pi orbital, because they look like a p orbital when they view along with the bond. So this is the 2 pi x and 2px and 2px molecule, and there is the pi bonding and there is a pi antibonding. So this kind of bonding occurs in the pi bonding. So for the pi bonding, the 2px orbitals are present, and this orbital will overlap and form a pi bond in a molecular orbital. So next is you can see the sharing of p and s orbital of mixing. So there is a diagram of this is the energy here. You can put the energy here, and this is the 2s and this is the 2p of M.O.s, and this is the 2s and 2p for the M.O.s. Now you can see in this diagram the for the 2s orbital you can see the bonding and antibonding here, and for 2p you can see the bonding for the pi, for the sigma, and the pi antibonding and pi sigma antibonding. Okay, so but in this diagram you can see the 2s bonding and antibonding, and for 2p you can see that the pi bonding for x and y, okay, and the sigma for 2p. And here you can see the pi, it is different from the tetrahedral and octahedral, for the octahedral and tetrahedral. So this is the antibonding for the pi, and this is the antibonding of the sigma orbital. So for the molecular orbital diagram, if we see for the H2 molecule, you can see here that this is atomic orbital, the 2 atomic orbital, and the molecular orbital having the 2 electron form bonding and antibonding. Okay, this is the bonding and this is the antibonding, and this is the energy for the energy level of the orbitals. Now if you can see the molecular diagram of N2 molecule, you can see the s orbital and you can see here the p orbital. So the p orbital you can see the pi bonding and sigma bonding, and there is a pi antibonding and sigma antibonding. Okay, for molecule of O2, you can see the s orbital and the px by z orbital. Here is the sigma bonding, the pi bonding, pi antibonding, and sigma antibonding orbitals. So the M.O. of the polar covalent bond like HF are in this kind of molecule, the energy level of 1s and 2s is if you see the energy level is a difference. So what happened, the sigma bonding of mostly occur in a HF bond, like the one electron from s orbital and one electron from fluorine to p orbital combine and